Very good morning. I welcome you all in this lecture of energy engineering. In this lecture, we will solve a numerical problem on a regenerative Rankine cycle. First of all, we'll see problem and then we will solve it as such. A steam power plant, a steam power plant operating on a steam power plant operating on ideal regenerative Rankine cycle. Ideal and regenerative Rankine cycle. Ideal and regenerative Rankine cycle with one open feed water heater. So open feed water heater arrangement is there in order to have ideal and regenerative Rankine cycle. Steam enters the turbine at 150 bar and 600 degree centigrade temperature and is condensed at a pressure of 10 kilopascal. So initially steam pressure is 150 bar and steam temperature is 600 degree centigrade, and then it is get condensed at a pressure of 10 kPa. Steam is bled at 12 bar, so intermediate pressure is at 12 bar and it enters the open feed water heater. Determine the fraction of steam extracted from the turbine and thermal efficiency of the cycle and specific steam consumption. Consider pump work, and we have to use steam table only here. Cp of steam is given, that is a 2.1 kilojoule per kg Kelvin. Now first of all we will write whatever the things are given, and here we have to use steam table only. So before solving the problem we will see how is the ideal regenerative Rankine cycle. So ideal regenerative and regenerative Rankine cycle. How is the ideal and regenerative Rankine cycle? I am just trying to draw the ideal regenerative Rankine cycle. So this is the pump. So this is boiler, this is turbine, this is pump 2 we have, and this is open feed water heater. This is open feed water heater, this is second pump, and here we have another pump, that is pump 1, and we can draw condenser here. So this is condenser, this is pump 1, so these are the different elements in a regenerative Rankine cycle. Now when I am considering turbine, we are considering this as a HP and this as a LP turbine section as such. Now as we are considering that before entry to the turbine the steam pressure and temperature is 150 bar and 600 degree centigrade, and the state of the steam I am just expressing with the thermodynamic state point 1. So this is the thermodynamic state point 1, and up to this point I have the second thermodynamic state. Here I am considering third thermodynamic state, here I am considering fourth thermodynamic state, here I am considering fifth, here I am considering sixth, and here I am considering 7th. Now as we are bleeding the steam, we are extracting the steam to the open feed water heater, and then steam get mixed with the condensate whatever we are getting from the condenser, and the same mixture we are pumping with the help of this pump to the boiler. So apart from this, the very important thing is that I am considering that 1 kg steam is continuously flowing. 1 kg per second steam I am considering is that continuously flowing through the circuitry as such. So the same 1 kg steam this pump 2 is handling, same boiler flow through the boiler is there, that is of 1 kg per second, and this turbine, that is the HP stage of the turbine, is also handling 1 kg. But now at this point certain amount of steam we are bleeding, that is I am considering m kg. So remaining 1 minus m kg steam is we are expanding through this LP turbine, and same steam, that is 1 minus m amount steam, is also flowing through the condenser and pump 1, and then this m kg and this 1 minus m kg steam mixes with each other in this open feed water heater, and further cycle goes on continuing over here as such. So this is the ideal regenerative Rankine cycle, as we are saying. Now apart from this, I have the steam which I am bleeding is at a pressure of 12 bar as given, and the pressure of the steam at the outlet of the LP turbine is a 10 kPa, is a 10 kPa. Now these are the different things given in the problem. Now the another thing that we can concentrate is the pump 2 is requiring WP2 work, this pump 1 is requiring WP1 amount of work. Then this this whole flow diagram we can represent on TS diagram also. Then how we can represent this whole flow diagram on TS diagram, we will just see. Suppose this I have TS diagram for this ideal regenerative Rankine cycle. Again I am considering this as a dome region, very short small space is available for drawing the diagram, but you can understand this is the process 4 to 5, this pump 1 4 to 5, then this is feed water heater, this is the feed water heater 5 to 6, again pumping is there, again feed water heating, and this is the constant pressure heat addition inside the boiler 7 to you may say 1, and 10 there is expansion. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So I am just showing with the help of arrows. These are the arrows to show the different processes. We can show with the help of these arrows. Okay, so this 4 to 5 is pumping, then this is the heat added at a constant pressure in, you may say, open feed water heater, then this is the pump 2 operation, this 7 to 1 is the heat constant pressure heat addition in boiler, 1 to 2 this is high pressure expansion, this is the low pressure expansion in a turbine, 2 to 3, then this one is the condensation, and this one is the bleeding of the steam, that is you may say open feed water heater, and this one is the point at which we are bleeding this steam. Now apart from this, this is the constant pressure, and this is 150 bar, this is constant pressure which is extraction of the steam at a 12 bar, and this is the condensation at 10 kPa as such. So this is whole thing regarding ideal regenerative Rankine cycle. Ideal and regenerative Rankine cycle. Now, what is the next thing that we have? That Cp is given, which is 2.1 kilojoule per kg Kelvin. Now, from this steam table, we get the following. What we will get different figures from this steam table. Now, when I have 150 bar steam and this point, the temperature of the steam is 600, so I can easily say that the steam is superheated at 150 bar, as the saturation temperature is lesser than 600 degrees centigrade temperature. So I can write at P1 is equal to 150 bar. From the steam table I can write Hg1 is 2615.1 kilojoule per kg. Sg1 is equal to 5.318 kilojoule per kg Kelvin, and Ts1 is 342.1 degree centigrade. So how much is the value of, as we have to use only steam table, so we have to note down Hg1, Sg1 and Ts1 from the steam table. So H1, that is enthalpy of this point H1. See, in case of any kind of Rankine cycle, our aim is to determine enthalpies at different state points, and then further calculation will be there. But now I am aiming here to get the value of H1. So H1 is equal to Hg1 plus Cp T sup 1 minus Ts1, that is equal to 2615.1 plus 2.1, which is given, into 600 minus 342.1. Okay, now with this I can write very important thing, that is how much is the value of this H1. I can calculate, that is 3156.7 kilojoule per kg. So I have the value of H1 now. Now further how we can proceed with the help of this. Now I can find out, with the help of this I can find out how I can find out the value of S1. S1 is equal to Sg1, properties of steam, Cp ln of T sup divided by Ts, that is Tsat, at 0.1. So that is equal to Sg1. From the steam table we have the value 5.318 plus 2.1 into ln of this, that is 600 plus 273 divided by 342.1 plus 273. So I will have the value, it is 5.668 kilojoule per kg Kelvin. Further I can find out, this is whole things are occurring at 150 bar. Now I have at P2 is equal to 12 bar. P2 is equal to 12 bar. So how much is the value of HF2? From the steam table, HF2 is equal to 798.4 kilojoule per kg. I am just listing this value. HFG2 is equal to 1984.3 kilojoule per kg. SF2 is equal to 2.216 kilojoule per kg, and SFG2 is equal to 4.403 kilojoule per kg. Further, I am just listing the properties which we have. Further I can write at P3, which is equal to 10 kilopascal or 0.1 bar, I can write HF3 is equal to, or H4 is equal to 191.8 kilojoule per kg. HF G4 or G3, third point, is equal to 2392.8 kilojoule per kg. SF3 is equal to 0.649, that is kilojoule per kg Kelvin, and SFG3 is equal to 7.501 kilojoule per kg. Now with this I am considering isentropic process. As we know that isentropic process, isentropic expansion, that is reversible adiabatic expansion in a turbine, that is 1 to 2. In high pressure turbine we are considering S1 is equal to S2 is equal to SF2 plus X2 SFG2, X2 into SFG2. So I have 5.668 is equal to 2.216 plus X2 into 4.403. So I have the value of X2 with the help of calculation, that is 0.784. With the help of this I can find out H2. H2 is equal to HF2 plus X2 into HFG2, very simple, that is equal to 798.4 plus 0.784, which are given these values. 798.4 plus 0.784 is this, into HFG2, that is 1984.3 kilojoule per kg. So I will find I will get the value, that is 2354.1 kilojoule per kg. In the same manner I can write here the process 1 to 3. For the process 1 to 3 I can write S1 equal to S3, and in the same manner I will get the value of X3. I am not writing everything now here in order to save the time. I am not writing everything, and I will get X3 value, which is equal to 0.6691. So as S1 is equal to S3 I will have SF3 plus X3 into SFG3. I know the value of this SF3, SFG3 and S1. So unknown X3 I will get as a 0.6691. So H3, with this I can find out the value of H3. H3 is equal to HF3 plus X3 into HFG3, that is H3 is equal to, we will get H3 from this. So H3 is equal to 191.8 plus X3, which is 0.6691 into this into 0.6991 into this HFG3 is a 2392.8, and from this I will get the value of this H3. H3 is equal to H3 is equal to 239. H3 is equal to 1792.8 kilojoule per kg. So now here I have the value of H3, value of this H2, value of this H2, and initially I have the value of H1 also. Now I have the value of H1, I have the value of H2, I have the value of H3 in my hand. Now with this lot of work, with this work I can move further with to get the value of pump work. So I am writing pump works as two pumps are there. I am writing first pump work for first pump, that is P1 minus PB, these are the relations, divided by 10, which is equal to 12 minus 0.1 divided by 10. Pump work for the first pump is 1.2 kilojoule per kg. Then with this I can write H5 is equal to H4. This is H5 minus H4 is the first pump work. So this is pump work first. This is the pump work is equal to H5 minus H4. So I am getting H5 is equal to H4 plus first pump work, that is 191.8 plus 1.2, which is equal to 193.0 kilojoule per kg. The second pump work is again in the same manner, P1 minus P2 divided by 10 is equal to 150 minus 12 divided by 10 is equal to 13.8 kilojoule per kg. From this, in the same manner, I will have H2 minus H6 plus second pump work, which is equal to 798.4 plus 13.8, which is equal to 812.2 kilojoule per kg. Now I don't think that there is any problem in understanding this. Only enthalpy difference and pressure difference at the 2 points during that particular pumping process we have to consider to get this different value of H5 and H6. So now as we have the value of H1, H2, H3, H4, H5, and here I have the value of H7, this is H7, this is H5, and this is H7. So with this initially we know the value of what you may say H4 and H6, because H4 and H6 are lying on the saturated liquid line as such. Now with this, now we can find out whatever is the asked in the problem, that is first that they have asked, the first thing they have asked, that we can calculate with the help of this. The first thing they have asked, that is fraction of steam extracted from turbine. Fraction of steam extracted from a turbine. Again we require here energy balance. So how we can do the energy balance, that is energy into feed water heater equal to energy leaving the feed water heater. Energy leaving the feed water heater. Energy into feed water heater, energy leaving the feed water heater. This is the energy balance. So again I have M into H2. This is the energy entering into the feed water heater, that is the mass flow rate into enthalpy, plus 1 minus M into H5, that is equal to 1 into H6. This is very easy. So again I am putting the values of respective enthalpy. M into H2, that is 2354.1 plus 1 minus M into 193.0 is equal to 1 into 798.4. With this I can find out unknown M, that is 0.228 kg per kg of steel. So this is the first answer. Second, they have asked thermal efficiency of the this power plant, thermal efficiency of this plant. So to get the thermal efficiency is what? It is a shaft work divided by heat supplied. So to get the shaft work, how we can find out shaft work? That is turbine work, which is high pressure turbine, that is another turbine is the low pressure turbine, minus 1 minus M, that is the pump work. The first pump is handling 1 minus M amount of mass flow rate, and second pump is handling whole mass flow rate, that is into 1. So this is the way to get the value of shaft work. So first I can write first turbine work, that is HP turbine work, is 1 into H1 minus H2 plus this low pressure turbine work is again 1 minus M H2 minus H3 minus 1 minus M into first turbine work minus 1 into second turbine work equal to, again I am putting the enthalpy value, 1 into 3156.7 minus 2354.1. These are all enthalpy values I am substituting here directly, which is not difficult to understand. 2354.1 minus 1792.8 minus 1 minus 0.28 into 1.2 into 13.8. So this is very important to have to obtain the value of pump work, that is 1192.0 kilojoule per kg of steel. Now heat supplied, that is heat supplied in boiler, that is QS is equal to H1 minus H7. This H1 is a 3156.7 minus 812.2. So heat supplied I will get 2344.5 kilojoule per kg. Now further thing is the efficiency. Efficiency is the shaft work divided by heat supplied. So that is 1192.2344.5, that is 50.84 is the shaft work, is the efficiency, sorry. So next, third that we have to work out, this is the second answer. The third thing that we have to work out is the steam rate or specific steam consumption, which is 3600 divided by shaft work, and we are expressing it in a kg per kilowatt hour. So now I have this 3600 at the numerator divided by shaft work, which is 1192, So I will get it as a 3.02 kg per kilowatt hour, kg per kilowatt hour, which is the shaft work as such. So this is all about how to solve the problem, of related to ideal and ideal regenerative Rankine cycle. In this problem, it is very important to understand how the fraction of steam we are extracting, and how to utilize that energy balance equation, that is energy into feed water heater, and which is equal to energy leaving the feed water heater, because it is very important to get the value of M first. Then other things are very similar to the generalized problem, that is to get the plant efficiency and specific steam consumption or steam rate. So with this, today we are stopping here, and I hope you will ask me if you will have any query in future also. Thank you very much.